So whereabouts would we need this situation where we need to drive that base current so hard that we saturate the transistor? Well, one instance would be where we have a lamp in the transistor circuit. Here's our 4K7 perhaps, or maybe even a lower value of resistor there, 12 volts. And if we don't saturate this transistor enough by putting effectively a short circuit across there, this lamp is not going to light up brightly. And also, not only is it not going to light up brightly because we haven't got the maximum current that lamp requires, but this junction, if we don't fully saturate the transistor, is going to behave like a resistor, and resistors get hot. They give off heat, so the portable transistor starts to cook. The thing is about saturating a transistor and running it in saturation is that the transistor power dissipation becomes effectively quite low because we're not losing any heat across that junction because the junction resistance gets quite low. Alright, so we're not doing this in the circuit that we're working with. This particular application would be called using the transistor as a switch. Using the transistor as a switch. So the important considerations are the selection of the transistor. Can the collector-emitter junction continuously carry that amount of collector current? That's something that can be found in the transistor specification sheets. And also the saturation current that we need in the base. So we need to find out the beta of the transistor, and then we can work from what we require in the collector circuit, divide that by the beta, and find out the effective base current that we need to saturate it, and then we can do as we did before I cleaned the board, and we can work out the value of the base resistor, and we found out before that we needed 720k in that base circuit. But today what we're going to be more concentrating on with the transistor is working in the active region for some amplification. And what we're going to finally have today is a transistor amplifier that has a bit of distortion in it, and we'll find out why as we get further into the lesson. So something that we have to learn right at the beginning here is this graph, and this graph represents the voltage between the collector and the emitter, and over here IC. And there's two important points that we can plot on this graph, and one is VCE off, and the other one up here is IC sat. We saw IC saturation. When we saturate that transistor, what's the maximum collector current going to be? And then what we can do with these 2 points, we can draw a nice line on our graph down through there. Our old green pen's not as good as it could be. Let's stand him on his end. Other things to note here are this is going to be VCE equals 0 at this point here. So these represent all the ranges from VCE 0 up to VCC, because when VCE is off, the transistor is turned off, VCE actually has the full rail voltage on it, because if I come back to this transistor and we cut that emitter, and then we think about getting a voltmeter and putting the voltmeter between here and between here, what am I going to measure on the voltmeter? Well, if inside the transistor has been like cut and there's nothing, there's just an open circuit there, and the voltmeter has extremely high R internal, a very high internal resistance of maybe, if it's a digital multimeter, 10 million ohms, 10 mega ohms, we're effectively going to have no current flowing in this circuit. Very, very minuscule current. And if you don't have current flow, you can't have voltage drop across the resistor. Now I've got 4.7k resistor here. Let's get rid of our light bulb in this situation, just to make it simple with one resistance. 4.7k, let's say I've got, I don't know, 10 picoamps of current flowing. How much voltage drop have I got across that resistor? I've got no voltage drop across the resistor. So therefore, at that point there, I'm going to have plus 12 volts. Plus 12 volts, plus 12 volts. So the meter's going to measure plus 12 volts when the transistor is cut off. Cut off. The transistor is turned off, there's no base current. But of course, we put that back in, and if we put our trusty resistor back up there to plus 12 volts, and we saw before that we needed 720k to saturate the transistor, and saturate means a short circuit across there, we'd get VCE equals 0. So this is going to be at saturation. And that's at cut-off. So what about if we put a value somewhere in between with this resistor? What if we put a resistor there which is about, I don't know, 2 meg ohms, 2 million ohms? We're going to be somewhere along this axis. We're going to be there. And this load line here allows me to say I'm going to have that much voltage measured between VCE with that base current. Therefore, it intersects the load line, and the load line I can come across, and it tells me exactly how much collector current that I'm going to have for that value of base current. Now, when you look in the textbook has a lot of different values for base currents. IB equals something. IB equals something. And this is by the manufacturer. They give you this set of curves, characteristic curves for the transistor. And if IB equals a certain value, you can say, well, that's going to give me that much IC, and it's going to intersect the curve over here, the load line rather, over here, so that I'll have that much IC and I'll have that much VCE for that value of base current. Not all the time do you have these characteristic curves though. We today found out what the beta of the transistor was, and we worked backwards from the maximum collector current, and we played with the base current that way. We found out what the base current at saturation was. In fact, I think saturation base current we needed 9 microamps. So on these characteristic curves, if we just come up here and put one more on, this would have to be, I think it was 9.1 microamps we had, and that reflects here saturation current for the transistor. But remember what we said about using different transistors in the circuit, and the fact that there is individual variation in beta with transistors. So we chose that value of 720k, I think we had, and that was to guarantee that we actually put that transistor into saturation if we want to run a load like a light bulb in the collector circuit. But any of these values today below 9.1 microamps are going to put us at different values down the load line and take us from where we've got VCE equals 0, short circuit situation under saturation, up to VCE off, the transistor is cut off, so therefore we actually have the full rail voltage there, because in cut off there's no collector current. No collector current means there's no voltage dropped across the 4.7K resistor, therefore the multimeter measures the full value. You can start to see here, or appreciate why all the teaching that was done in the DC circuits subject really comes into play here. All those important things like understanding Kirchhoff's current law and Kirchhoff's voltage law really do come into their own when we start analysing transistor circuits. All right, end of part 2.